everyone, and welcome to This Explainer. Today, we're unpacking what honestly might just be the most profound technological shift of our entire lifetimes. We're talking about massive geopolitical stakes, hundreds of billions of dollars, and a global race to master a technology that fundamentally bends the rules of physics. Look, this isn't just about getting a faster processor or some fancy upgrade to your laptop. It's a completely new paradigm, one that embraces the strangest, most mind-bending behaviors of the subatomic world to do things we literally thought were impossible. So welcome to the dawn of the quantum computing revolution. Let's dive in.
To really understand why world governments and tech giants are just so incredibly obsessed with this right now, we have to start with a seemingly simple question. How do you solve the unsolvable? I mean, today's absolute fastest supercomputers are absolute marvels of human engineering, right? They can perform quadrillions of calculations every single second. Yet, even with that mind-bending speed, there are certain incredibly complex problems. We're talking deep mathematics, chemistry, cryptography, that would still take our most advanced classical supercomputers millions or even billions of years to crack. Why? Because at the end of the day, classical computers are linear. If a classical computer is looking for a specific password, it's kind of like a person trying a billion different keys on a keyring, just one by one by one. Sure, it does it incredibly fast, but it still has to check every single wrong answer before finding the right one.
Okay, so let's get into the incredible paradox at the heart of our explainer today. On one side, we have the absolute ceiling of our current technology, literally billions of years to solve these complex linear problems. But on the other side, we have the promise of quantum computers, solving those exact same problems in mere minutes. I mean, how is it even possible to condense billions of years of processing into the time it takes to grab a coffee? To really grasp this monumental leap, we basically have to completely throw out our understanding of what a computer actually is and acknowledge the physical limits of our current world.
Part 1. From classical to quantum. So, our classical computing world kicked off back in the 1940s with the invention of binary bits and transistors, and by the 1960s, we had Moore's Law, which basically dictated that chips would just keep getting smaller and more powerful every couple of years. But we're hitting a massive problem today. Classical computing is currently slamming into a physical brick wall. Today's transistors are approaching the size of single atoms. You simply cannot shrink them any further without the laws of classical physics completely breaking down. When things get that small, electrons start behaving erratically, literally teleporting through barriers in a process called quantum tunneling. So classical chips basically stop working. But what happened next actually surprised even physicists. Instead of fighting this weirdness of atomic physics, scientists looked back to the 1920s, to the birth of quantum mechanics by genius minds like Planck, Heisenberg, and Schrödinger. They realized this strange subatomic science could actually be harnessed as a tool. Fast forward to the 1980s, and visionary physicist Richard Feynman proposes building a computer that didn't just calculate quantum physics, but actually operated on those very rules.
Part 2. Entering the quantum realm. Let's see how this works.
Crossing into this microscopic world means leaving pretty much everything you know about standard computing logic behind. The entire foundation of this new logic is the qubit. This is the fundamental unit of quantum information. So, while a classical computer uses traditional bits made of silicon transistors to process information, a quantum computer uses qubits. And a qubit isn't just some physical switch. It is often an actual physical particle. Think a single electron, an ion, or even a photon of light, which is isolated and manipulated to leverage the bizarre laws of quantum mechanics. And this is the kicker. It allows the qubit to represent multiple states at the exact same time.
To really grasp the difference here, think of a classical bit like a standard light switch. It's always absolutely off or on, right? A 0 or a 1. But a qubit, thanks to a mind-blowing quantum property called superposition, can exist as a 0, a 1, or crucially, both simultaneously. It's like, think of that classical bit like a coin sitting flat on a table. It's either heads or tails. A qubit, on the other hand, is like a spinning coin. While it's spinning, it is essentially both heads and tails at the exact same time. This seemingly simple little change unleashes exponential power. With classical bits, 2 bits equal 2 bits of data. But with qubits, the power scales exponentially. 2 qubits can represent 4 states. 3 qubits can represent 8 states. By the time you string together just 300 perfectly functioning qubits, they can simultaneously represent more states than there are atoms in the observable universe. It's honestly hard to even wrap your head around.
But superposition is really just the beginning. It's just the spinning coin. To actually compute anything, you need a few other core mechanics. Next up is entanglement. This is what Albert Einstein famously called spooky action at a distance.
It means two or more qubits become intimately linked together no matter how far apart they are. If you change the spin of one qubit, its entangled partner reacts instantly. This allows quantum computers to tie particles together into massive synchronized processing webs. Then we have quantum interference. If you think of a quantum computer trying millions of paths simultaneously, interference acts kind of like noise-canceling headphones. It manipulates the probability waves so that all the incorrect answers actively cancel each other out, leaving only the correct answer amplified right at the end. And all of this is steered by highly specialized quantum gates. Now, a very important takeaway here. Because of these highly specialized mechanics, quantum computers are absolutely not here to replace your traditional laptop. They operate on entirely different logic, designed for a completely different class of massive problems.
Part 3. The multi-billion-dollar race.
Knowing this immense, universe-altering potential, it makes sense that we are now witnessing a massive global scramble. Governments, elite universities, and major tech companies are currently locked in a fierce race to master this strategic technology. We are talking about hundreds of billions of dollars in global quantum investment. This is definitely not just some niche academic pursuit anymore. It is viewed as a totally critical matter of economic dominance and national security. Superpowers like the United States and China are investing heavily because they recognize that whichever nation masters stable quantum computing first will hold an absolutely insurmountable advantage in intelligence, defense, and global technology.
Now, what's really fascinating here is where all this money is actually coming from. It's a three-pronged attack. First, we have massive public and government funding driving those national security and defense interests we just talked about. Then, you've got aggressive private investment and venture capital backing these incredibly agile, risk-taking startups. And finally, corporate tech giants are pouring unprecedented resources into their own internal R&D. This intense global competition has created an absolute frenzy for talent, resulting in a massive workforce demand for specialized quantum physicists, material scientists, and engineers.
But behind every theoretical breakthrough is a staggering engineering challenge, because, honestly, nobody knows the best way to build a qubit yet. So labs around the world are placing multi-billion-dollar bets on completely different hardware architectures. Some are building superconducting qubits, which rely on loops of specialized metal chilled to near absolute zero so electrical current flows without resistance. Others rely on trapped ions, using precision lasers to suspend individual electrically charged atoms in a total vacuum. You've also got teams working on neutral atoms, moving uncharged particles around with highly focused optical tweezers. And then there's photonic computing, which attempts to run calculations using literal particles of light flying through microscopic silicon channels. It is wild stuff, and nobody knows for sure which hardware architecture will ultimately win the race.
Part 4. World-changing applications.
So what is this monumental mountain of investment actually trying to achieve for humanity? We are talking about centuries of progress condensed into a matter of days. Take drug discovery, for example. Right now, classical computers can only roughly approximate how complex molecules interact. A quantum computer could simulate exact molecular interactions precisely as nature intended, leading to perfectly personalized medicine and cures for diseases we currently just can't model. In material science, they could test millions of chemical combinations instantly to design lighter, stronger aircraft or, the ultimate long-lasting battery. They could instantly optimize global supply chains, run impossibly dense climate and weather predictions with absolute pinpoint accuracy, and propel artificial intelligence into a completely new stratosphere of capability by training models in fractions of the time it takes today.
However, let's make sure we keep our feet firmly on the ground here. This timeline really separates the hype from the reality. In the present day, we are still very much in the early research phase, largely running small-scale algorithms on incredibly noisy machines. It won't be until around 2030 that we expect medium-term, what they call fault-tolerant milestones. Fault-tolerant simply means the computer can finally run without its own internal environmental noise, constantly ruining the mathematical calculations. Once we achieve that, those massive world-changing applications like advanced AI and precise climate modeling actually become possible. But again, those remain long-term goals, looking out toward 2050 and beyond.
Part 5. The hidden hurdles. Almost nobody knows about the monumental roadblocks actually standing in the way of that 2050 timeline. The main challenge is just how unbelievably fragile qubits are. To engineer the impossible, you have to follow incredibly difficult steps. First, many of these systems require extreme cryogenic cooling. We are talking a fraction of a single degree above absolute zero. That is significantly colder than the vacuum of deep space. Step 2 is preventing something called decoherence. The absolute slightest vibration, A stray microwave or even a microscopic fluctuation in temperature causes the qubit to instantly lose its quantum state. It collapses back into a normal bit and completely ruins the calculation. Finally, step 3. Researchers must achieve scalable error correction. They have to build systems where hundreds of regular qubits work together just to act as one single, perfectly stable logical qubit. It is a monumental task.
So when we weigh the massive hype against the current reality, these challenges are severe. Today's early machines suffer from crippling error rates due to that decoherence problem. The energy consumption and the sheer cost of running those massive cryogenic systems is astronomical. Plus, as we mentioned, there are severe talent shortages across the globe. But perhaps most alarmingly, there are massive national security risks tied to cryptography. See, nearly all modern encryption, banking, private messages, state secrets, relies on the fact that classical computers take millions of years to factor massive prime numbers. But a fully functioning quantum computer utilizing a specific mathematical tool called Shor's algorithm could factor those numbers in seconds. It could theoretically shatter the cryptographic encryption that currently protects all of the world's secure data, simultaneously. It's a huge deal.
Part 6. Future Outlook. Despite these massive engineering hurdles, the momentum here is entirely unstoppable. Looking at how this builds over the coming years, we can ground our predictions in current industry trends. By the 2030s, experts predict we will finally see those fault-tolerant quantum computers emerge, machines capable of actively correcting their own errors on the fly. By the 2040s, we'll likely see the rise of hybrid cloud services, so you won't have a quantum computer sitting on your desk. Instead, classical servers and quantum supercomputers in the cloud will work together seamlessly, passing data back and forth to solve different parts of a single problem. And by the 2050s, we anticipate the development of a secure quantum internet, a communication network relying on entangled particles that would, by the very laws of physics, be completely unhackable.
Bringing our story full circle, this is really the most important takeaway of our entire explainer today. Every major computing revolution in history has expanded our ability to solve previously impossible problems. Quantum computing isn't about making your smartphone load web pages faster or getting higher frame rates in a video game. It is an entirely new paradigm, leveraging the deepest, most hidden mechanics of the subatomic universe, designed specifically to solve the incredibly complex problems that classical computers simply never could.
History remembers the inventions that change how we live, but some technologies change how humanity understands the universe itself. Quantum computing is exactly that rare revolution. We are standing right at the threshold of an entirely new era of human capability. But it really leaves us with one massive question. When that switch is finally flipped and a fully stable quantum computer comes online, are we truly ready for the answers it will give us? Thanks for joining me on The Explainer today. I'll see you next time.
Thanks for watching World Decoded. Make sure to like and share, subscribe, and stay curious.